Welcome back. In this session, we'll continue with the discussion on phase analysis. Now, as we told in the previous session that the impedances follow same rules as resistance. So let's find the impedance of a circuit, okay, that is composed of capacitors and inductors. Let's consider a circuit. I have a capacitor here, a resistor, another capacitor here, then we have an inductor, and we have a resistor. And the value of these are, the value of capacitor is 2 millifarad. The resistance is 3 ohm. And then capacitance is 10 millifarad. This is 0.2 Henry and 8 ohm. And our goal is to find the input impedance or impedance of this circuit at this. Let's call it Z. Okay. Our goal is to find the input impedance, and assuming this circuit is operating at a frequency omega, and that the circuit is operating at a frequency of 50 radians per second. Okay. Now remember, impedance is a function of omega. As omega changes, impedance of the circuit will also change, because we saw in the previous session the impedance offered by capacitor is simply 1 by j omega c. Similarly, the impedance offered by an inductor is j omega L. So as omega changes, the impedance offered by these elements will change. So what we'll do, we'll replace this circuit by it as phasor equivalent. Okay, so we'll draw it as phasor equivalent here. So, we'll redraw this here. So we'll replace this capacitor by this phasor value. Similarly, this inductor here. Then there is a resistor here. And we have one more capacitor. And we have a resistor here. So let me write the values of these. Now what will be 2 farad, 2 millifarad capacitor replaced with? The capacitance, this impedance offered will be 1 by j omega c, where c is 2 millifarad. So if we substitute the values, 1 j omega is 50, c is 2, and my millifarad minus 10 is 1 minus 3. So this value comes out to be equal to, so 550 into 2 into 10 is 1 minus 3 is simply 1 by j is minus j in the numerator side. It will be 10 minus 10j. So the capacitance, this impedance offered by this element is simply minus 10j. Similarly, the impedance offered by 10 millifarad capacitor will be simply equal to 1 by j omega c. Here c is 10 millifarad. So it will be 1 by j, omega is 50. How much is c? C is 10 into 10 is power minus 3. So this will be, this is simply equal to minus 2j. 500, yes, it will be minus 2j. Similarly, the impedance of, so what is the impedance offered by this capacitor? Minus 2j. Impedance offered by resistor will be 3. Impedance offered by this resistor will be 8 ohm. And what's the impedance offered by the inductor? Inductance is 0.2 Henry. So the inductance offered by 0.2 Henry will be simply equal to j omega L. J omega L is simply j omega is 50 multiplied by 2. So that is 10j. I think it is correct. Yes, 10j. Okay. Now, so this inductor will replace with 10j. So we have replaced the circuit by its phasor equivalent. Our goal is to find the input impedance. Now, in the previous session, we discussed that impedance follows all the rules of resistance. Means if there is resistance add in series, impedance is also add in series. If the impedances what happens to the impedance in the resistance in parallel, same thing will be applied for impedance. So what we'll do, we'll see first of all, we have a series connected impedances. So what we'll do, what will be the equivalent of these two? It will be simply 8 plus 10J. Similarly, we have a series branch here, 3 minus 2J. Okay, so what will be the equivalent impedance? So what will be the equivalent impedance of 8 ohm and 10J? Because these are connected in series. So let's call the impedance as Z1. So Z1 is simply 8 plus 10J, addition of two complex numbers. Similarly, 3 and minus 2J are in series. So 3 ohm and minus 2J are in series. So let's call the equivalent impedance as Z2. Z2 is simply 3 minus 2J. So if I redraw this equivalent circuit, we have a capacitor that offers an impedance of how much? Minus 10J. So minus 10J, will keep it like this. Then what we'll do, we'll replace these by the black boxes and this by another black box. If we don't know what is the element inside, so we write simply, so this is Z2, this is Z1, where Z1 is this and Z2 is this. As you can see, Z1 and Z2 are not now connected in parallel. So what will be the equivalent impedance? So equivalent impedance of these two will be simply, it follows the rules of resistance. So it will be Z1 multiplied by Z2, Z1 plus Z2. Right? So if two resistances are connected in parallel, we know the equivalent resistance is R1 multiplied by R2, R1 plus R2. Okay, same rule will apply here. Okay, so substituting the value of Z1 and Z2, Z1 is simply 3 minus 2J, I think. Yes, 3 minus 2J, and Z2 is 8 plus 10J, right? So 8 plus 10J, yes. So this will be 3 minus 2J plus 8 plus 10J. Okay, now these are mere complex numbers. So if you know how to manipulate complex numbers, you will be able to solve this. Okay, let's solve these in rectangle form. Okay, first. So let's keep them and multiply the numerator and add the denominators. So 3 8 is 24, then 3 10 is 30J, then minus 2J multiplied by 8 is minus 16J, then minus 2 multiplied by 10 multiplied by J square, J into J is J square, then 3 plus 8 is 11, then minus 2J plus 10J is plus 8J. So if you simplify this, those will be 24, then 30 minus 16 is 14J, then this will be 2 into 10 is minus 20, and J square is minus 1, so it will be plus 20 divided by 11, 8J. Okay, now so 20 plus 24 is 44 plus 14J divided by 11 plus 8J. Okay, so what we will do now, we can convert these numbers into the polar form and do the division of these numbers, or we can also do one more way. We can do the rationalization. Now, how do we do the rationalization? Then multiply the numerator and denominator by this 11 plus 8J is conjugate. So that's how we do rationalization of complex numbers. So if it is plus J here, we'll multiply it by minus times. Okay. So if you now do the multiplication of numerator and denominator, so it will be 44 multiplied by 11 is 484. Please check this calculation. And then 44 minus 8J is simply 352J. 14 plus 11 is, I think, 154J. And then 14 minus 8 into 14 is 112. Then J into J square. So it will be 112 plus 112. Okay. Why plus? Because J and J square. So then in the denominator we have 11 square. And then plus 8 square again. Why? This is A plus B, A minus B. So it will be A square minus B square. But since we have J square is minus, so it will become plus. That's why here it is plus. Okay, here it is plus. All right, so let me continue this. So how much is 484 plus 112? That is 596 minus then 352 plus 154 is, I think, 198J divided by how much is this? 11 square plus 8 square is 185. Please check the calculations one more time. So what is the result? So the equivalent of these two is 3.221 minus 1.07 J. Please check the calculation. So this is the equivalent of these two parallel impedances. So we'll replace this by a single impedance. So if we redraw this circuit, we can try it like this. Then we have an impedance. That impedance is equal to 3.221 minus 1.07 J. And we have here minus 10 J. So this is our circuit. We reduced our circuit to this. Now we can say these two impedances are in series, you can see. So what will be Zn equal to simply? Zn will be simply minus 10J plus, right? So impedances add in series. This impedance plus this impedance, okay? So this is our Zn. So Zn is simply 3.221 minus 11.7 J. So this is the impedance offered by the circuit at frequency of 50 radians per second. And see, so our goal was to find the impedance of the circuit at. So what we did, we combined these two impedances first, right? These two here. Once we convert it into phasor domain, we convert this, added these two impedances, then these two impedances, then this whole impedance and this impedance comes in parallel. Okay, then we do use the parallel law and we obtain the impedance is equal to something like this. Please check the calculation yourself. Then we redraw the circuit and the equivalent impedance comes out to be this. So this is the impedance offered by the circuit at this. Okay. Now let's solve one more example based on this impedance concept. Okay, let's write an example. So example is this. 60 and we have a capacitor here and then we have an inductor here. Voltage source. Then this is 20 cosine of 4t minus 15 degrees. Okay, how much is the capacitance? 10 millifarad. How much is the inductance? 5 Henry. And our goal is to find V naught, voltage across this inductor. Okay, so what we'll do, we'll replace the circuit by the phasor. Okay. So what will be the phasor equivalent of this? 60 ohm will get replaced by 60 ohm. This capacitor will be replaced by 1 by j omega c and inductor will be replaced by j omega L. So this is our circuit. What is the phasor equivalent of this voltage source? It is 20 at an angle of minus 15. And this will be 60 and what will be 10 microfarad will offer an impedance of 1 by j omega c, 1 by j omega you can check is 4. And then C is 10 microfarad. 10 microfarad means 10 into 10 is minus 3. If you simplify this, this comes out to be 1 by j is minus j, so that is 25j. So we'll replace this by minus 25 minus 25j. Similarly, inductor will be replaced by j omega L. Omega is 4, L is 5, that is 20j. Okay, so this is 20j. And small v naught we will write as capital V naught. Okay. Okay. So we have to find this V naught across this impedance 20G. Now you can see this 20J and minus 25J are connected in parallel. Okay, that equivalent is connected in series with 60 ohm, right? So if we apply voltage division rule, we need to find first what is the equivalent of these two. So what is the equivalent of these two impedances? So let's find the equivalent of these two first. So what is the equivalent of 25 minus 25? So minus 25J is connected to parallel with 20J. So it will follow the rules of the resistance. So minus 25J multiplied by 20J divided by minus 25J plus 20J. This will be equal to minus 25J multiplied by 20J. How much is minus 25J plus 25J? Minus 5J. So from here, J and J will cancel. 5 is 25 and minus minus is plus. So the answer will be 500J plus J. Okay. So the equivalent of these two is now 100J. So let me redraw this circuit. If I want to redraw the circuit, I can draw it like this. Then we have an impedance. Okay. So what is this? This is how much? What is the source voltage? 20 at an angle of 15. So this is 20 at an angle of minus 15. So resistor has 60 ohm. And how much is this? This is 100J. Okay. Then we have to find what is V naught. V naught is now across this. Okay. V naught is across this parallel combination actually. And check it. So now we can use the voltage division rule to find V naught. So what will be V naught equal to? V naught will be equal to simply 100J divided by 60 plus 100J following the voltage division rule, then multiplied by 20. Source voltage is 20 at an angle of minus 15. Okay, so let's convert this. We have one in polar form. These two are in rectangular form. Let's convert all these in polar form. So V naught will be equal to 100. J is simply 1 at an angle of 90 degree. Then 60 plus 100J, it will be under root of 60 square plus 100 square. So that comes out to be 116.619. Please check the calculation is at an angle of 10 inverse 100 by 60. 100 by 10 inverse 100 by 60 comes out to be this much. Please check the calculations. Then we have 20 at an angle of minus 50. So let's first solve the numerator. So it will be 20 multiplied by 100 is 2000 at an angle of 90 minus 15. Angles will add. Why minus? Because this is minus 15. So 116.619 at an angle of 59.03. So V naught is 2000 divided by 100. 16 point. So please check this. This comes out to be 17.149. Please check the calculations. Then 90 minus 15 is 75 minus 59.03. Why minus? Because this is plus here. So on the numerator side, it will be minus degrees. Okay, so the answer is 17.149 at an angle of 15.97. Okay, please check the calculations. So V naught phasor, so voltage phasor across this impedance is simply this much. So what will be the time domain form of this? voltage. So V naught will be simply that is same as V naught of T is equal to amplitude is 17.149. What was the given voltage? Cos. Okay, we'll write cosine. Frequency is 4T plus 15.97 degrees. So this is the voltage that we needed to find across this parallel combination. So our goal was to find V naught. So what we did, we first converted this into the phasor equivalent, then we found the equivalent of these two impedances. Okay, then we used the voltage division rule that we learned from the resistor circuit. Okay, so in today's session, we learned how impedances are treated. Okay, how do we calculate the equivalent impedances of different elements? And based on that, we solve two examples. Now, here's an assignment from Sadiko's book, Alexander Sadiko's book. So what you do? Okay, fundamentals of electric circuits. Solve practice problem. First, you will solve practice problem 9.10. So you will solve this. This will help you to understand the concept of impedances further. And then you will apply the concept to another problem, that is practice problem. We'll solve practice problem number 9.11. So solve these two problems, you will understand the concept of impedances better. Okay, let me end this session here.